A baseball player hits hitting a ball, hitting a low pitch. So we're going to do the same problem. We're just going to throw in one additional wrinkle. All right, so just like yesterday, the baseball player hit the low pitch, but this time instead of the pitch going landing at the same height as it was hit from, now it lands in the stand. So we found that was sort of like a home run yesterday. So the pitch today, the ball today, lands in the stands. All right, and in the stands, I mean 10. We're going to say it's just 10 meters off the ground. All right, so the picture is really the same. All right, ball leaving the bat at, I think we said 40 kilometers per second at an angle to the horizontal of 60 degrees. Ball flies away from the bat. My picture is slightly different now, sorry. And it ends, this time, off the ground at a height of 10 meters. All right? So same sort of problem, slightly different conditions. So when I did this problem yesterday, I sort of cheated, right? Well, I didn't cheat, but I made use of the fact that the velocity at the peak of the trajectory is 0, the vertical velocity is 0, and the time it takes to get to the peak is 1/2 the time it takes for the whole trip. Well, I don't know that time relationship anymore, so I can't make that same claim that the time it takes for the ball to travel to the peak is 1/2 the time it takes to get from the bat to right here. In fact, that's not true. Okay, so we can't relate the time that it takes to get to the stands to the time it takes to get to the peak. So I can't do it quite the same way as I did before. All right, but that's okay. We can still solve this problem. And so we'll use the same general idea, and I'm going to write that down. T total this time does not equal to T peak times 2. Not the case this time. It's a really thick brush. Really thick brush. I think it's because of, I don't know if this is going to like it, minimum diameter. Yeah, I'll have to research that later. Okay. So I still want to know what is the range. I still want to know what the range of the ball is. What is the range? Actually, I know how to change it. All right, still what I'm after, same question, just a little bit different scenario. So in this case, I'm going to do just like I did yesterday. I'm going to start the problem off making a list, or making 2 lists, I guess. I'm going to write down what I know and what I don't in the x and the y direction. All right? So once again, I know the same thing as I knew yesterday, so let's just cruise through this. The initial velocity in the x direction, that's 20. This is not kilometers per second, because that ball would be trucking. That's meters per second. 20 meters per second. All right? Since we're doing projectile motion, the acceleration in the x direction is 0, which means the final velocity in the x direction is the same as the initial velocity in the x direction. Ax equals 0. I know my initial position. We're going to call that 0, x naught. And then I'm looking for x final. I'll leave that as a question mark. In the y direction, I know the initial velocity is equal to, what was it, 34.6. I do not know my final velocity. Now, yesterday, we made the statement that because the ball left and landed at the same height, namely 0, the y velocity and the initial y velocity and the final y velocity were the same, just in opposite directions. Right. This time we can't say that. The ball up here is not the velocity of the ball here, the speed of the ball here is not the opposite of the speed of the ball here. Would you say the speed of the ball in the y direction at this point is faster or slower than the speed of the ball when it leaves the bat? All right, it's got to be slower. Why? Because, well, I said when the ball gets to the ground, so imagine it keeps going, it gets here, the speed's the same. It's just the direction that's different. We know the ball must be speeding up towards the ground as it's falling, so that means back here it's got to be slower. So good. Good job checking your intuition. The acceleration in the y direction is what? Negative 9.8 meters per second squared. So beat these numbers into your head. Y initial is 0. Y final, we're not using F, is equal to 10 meters. All right, so there's my list. Again, I don't know anything about time. Time is an unknown. Okay, so once again, I don't know really anything in the x direction because these two numbers are the same and then I got a bunch of zeros. So I'm going to have to start in the y direction and figure out time. That's fine. I can do that. Yesterday, I just sort of had a little bit of a shortcut, and you'll see why here as we get to this equation. So we'll do it the y direction first. And what I'm after in the y direction is time. There are 3 different equations for time. I know a velocity, I know an acceleration, I know an initial position, and I know a final position. So I'm going to choose this equation. Y is equal to y naught plus Vy initial times t plus 1/2 at squared. Okay? I use this equation very often just because it tends to work out the most often, most frequently. All right, so I know this, I know this, I know this, I know this. I'm looking for t. All right, so y initial is 0, so I can get rid of that right away. I'm going to do this by plugging in numbers and then solving. A lot of the times I like to solve for variables. It's really up to you. Sometimes I think it's easier to check your work if you solve in terms of the variables instead of putting in numbers right away. But it's sort of, like I said, it's sort of up to you. I'm going to put numbers in first here, though. All right, so our final y position is 10 meters. I'm cheating and leaving off units right now. 34.6 is our initial velocity times time, plus, and I'm going to skip a step here. 1/2 times ay is negative 4.9, a number that you'll see quite a bit, times t squared. If I rearrange this and make it look a little bit more familiar, I get 4.9 t squared minus 34.6 times t plus 10 is equal to 0. Okay, and that's a quadratic. Right? Of course, it's a quadratic because we're describing the motion as a function of time. When we're dealing with projectile motion, the plot is a quadratic. It's a parabola. It makes a parabola, so that's what we expect. You have to solve this using the quadratic formula. So just as a quick refresher, that's A. We call this B. We call that C. And then I know that time then is going to be related to A, B, and C. How?
Negative B plus or minus the square root of B squared minus 4AC over 2A.
Good. Over 2A. All right, so that's our quadratic formula. If you do that, I'm sort of skipping steps here, but you get something like negative b, this is b, so it's 34.6 plus or minus. I evaluated the square root. If you do that, you get 31.6 divided by 2a, which is 9.8, back to our gravity. All right, so that's what you get if you do all the work of evaluating what's in the square root there. And if you solve for this, now there's a plus and a minus, so I'm going to get 2 answers. And so what you're going to get is you'll see one of those times is 6.76 seconds. Another one of those times is 0.30 seconds. So the real reason I did this example, which one? Which one's right? Huh?
You have to test them probably both.
Test them? Well, can we use our intuition here?
Well, yeah.
So here's the picture.
You can guess that it's 6 and probably be right.
All right. Well, what is 0.3 seconds? I mean, I would agree that the time it takes to get to this point is 6.76 seconds. Not only because that sort of makes sense, thinking about, you hit a baseball, how long does it take to get there, neglecting any sort of air resistance. And remember, this is going 400 and something feet. But we solved a problem yesterday, and the total time it took to get from this point to the ground was 7 seconds, right? Just over 7 seconds. So it's just a little bit short of the ground, so it should be just a little bit less time. But what is that other time? It's not the remaining time. Remember, this is the time that it takes for the ball to go from 0 meters to 10 meters.
Well, when you first did it, the first 2 meters, that's how long it takes to get to the...
Right, so here's our picture, right? This thing goes up and comes back down. It gets to 10 meters here, but it's also at 10 meters over here. So that time, 0.3 seconds, is the time it takes to go up to 10 meters. All right, and then on the way back down, 6 seconds later, that's when it's at 10 meters again. So the ball is at 10 meters twice. It's a quadratic, so there's got to be 2 roots if you're talking about math. So we have 2 solutions that work for this example, but we're looking for the far one, the longer time. So the correct answer is, I don't want that color, is 6.76 seconds. And that's because we want the solution when the ball is heading down. This is sort of refreshing, though. I mean, had we solved for the time it takes for the ball to go 10 meters vertically up, this same exact, nothing would have changed in our list over here. And if you think about it, this list would have been exactly the same. Y final still would have been 10 meters, so it's refreshing to know that, hey, physics works. The equations actually work. And, God forbid I'd actually tell you an equation that didn't work. That'd probably be bad of me. All right, so that's the answer. That sort of makes sense with everything that we've done so far. But I'm not done yet because I've only gotten the time that it takes to go the full distance. Now I need to actually solve for that distance. So now we can go back and look at the x direction. All right, and once again we can use our favorite equation, x equals x naught plus v naught, again vx naught, times t plus 1/2 at squared. There is no acceleration in the x direction, so that guy goes away right away. We said our initial position is 0. So now I can solve for a position just like I did yesterday. Our initial velocity is 20 meters per second, or time, 6.76 seconds. So x final is equal to 135 meters. All right. Again, I can check my answer based on what I know. We did that problem yesterday. I think we finished up with a solution of 141 meters. So it's just a little bit short, which seems reasonable, right? Because, of course, the ball hadn't quite reached the ground yet, hadn't gone as far. All right? Make sense coming together? Okay. Do I want to do 2 more examples, or do I want to do 1 more example? What do you think? 2 more? All right, you win. We're going to do 1 more example with numbers, then we're going to do 1 example without numbers. And we're going to make that one sort of a little bit more complicated. All right. Scrolling funny. There we go. All right. This one is, again, more baseball, because why not? It's baseball season. Let me write it. Pinwheel of doom. All right, so I'm going to write this one out. Got a fastball that you can throw a fastball pretty fast. A fastball can be thrown at 101.0 mph. So that's a pretty fast pitch. Not the fastest ever. The question is, if the ball is thrown horizontally, how far does it fall vertically by the time it reaches home? Whoop. Pay attention. Home plate. Yes, got it right. Okay. That one. No? That one. Okay. So the ball gets to home plate, you throw it, it's going to start to fall down because it's accelerating towards the ground. How far does it fall vertically? All right, so first step is to draw a picture. I think he's throwing like this. Who's your favorite pitcher? Who likes baseball here? 2 people. I'm a White Sox fan, as I alluded to yesterday, and I've always been a White Sox fan. So I was pretty excited when they won the World Series in 2005. But it sort of shames me, or it makes me frustrated, and this is how I feel about sports in general a lot of the time. I'm a huge sports fan. I'm a huge Michigan fan. But I was talking to my dad the other day. I'm like, I haven't gotten around to really following baseball yet this year because it's early and I'm busy and stuff. But I really don't know any of the players on the White Sox. I'm like, I can't even think. I'm like, okay, I know Paul Konerko because he's been around forever, but everybody else in the 2005 World Series has now moved on to somewhere else, and it just sort of makes me sad. Yeah, I mean, it's kind of a bummer. That's how it is. It is a business, and you can't really fault people for that, but it's a little bit unfortunate. At least with college sports, you sort of know, like, all right, 4 years and they're going to be gone. Maybe 5 years, or basketball.
2 years.
Basketball is a little bit different, but football, a lot of the times they got to stay around. All right, this is, I'm trying to draw it. This is kind of bad, but it looks something like this, where this is a nice parabola. Eventually, it falls, and that's horrible. I'm going to do that again. I don't like that at all. Eraser. Let's try that. It doesn't go up at all. It just sort of slowly goes vertical. All right, so that's what we're after right here. Where does the ball end? How high is the ball at that point? And the distance to the plate, home plate, is 60.5 feet. All right, so just like before, we need to make a list. I like to make lists. It seemed like when I was walking around yesterday, everybody was doing this, which was really nice to see. Hope you keep doing that on your homework. Definitely do it on your exam, because then I can give you partial credit if you don't get the answer right. Everybody likes partial credit. So our list, we're going to start off, I like to just go, let's write down everything. VXO, VX, AX. I know this is projectile motion, so the acceleration in the x direction is 0. Initial velocity and the x and the final velocity are the same. I did end up converting. Let's convert. All right. So 60.5. Oh, I'm sorry, velocity. We're doing velocity. 101 miles per hour. If you do the conversion, I'll just give it to you. 45.4 meters per second. Remember, I said it's just a little bit less than half when you're converting from mph to meters per second. Something good to have in the back of your head to impress your friends at the bar. Initial position, I get to decide. Final position, 60.5 feet. So we look at this and we're like, hey, I know everything in the x direction. That's pretty sweet. Too bad the question isn't about the x direction, because then I'd be done. Now we can look at the y. Initially, my y position is 0. My final y position, I do not know. My initial y velocity is 0. My final y velocity, I do not know. And the acceleration in the y direction is negative g. All right, cool. Now, by writing all this stuff down, I've defined a coordinate system. All right, now, so my question is, the reason I didn't write this explicitly, part of the first step, part of the drawing is to define your coordinate system. Now, I've chosen our normal x and y axis to be like so. Nothing new there, but where is the origin? All right, the origin is here, as I've chosen it. Okay? So, what does that mean I should expect my final y position to be? All right, so it's going to be negative because I'm solving from, if I draw this line out, these should match at first, but I'm solving for this distance, which I'm calling y, right? So that's why we want to make sure that we know what our origin is initially. I'm free to choose that wherever I want. I could pick here. I could pick right here to be my origin. Doesn't matter, but it doesn't really make sense to do that. I mean, I could do it. I just need to make sure that I adjust my distances accordingly, right? That's not a very logical place to do it, but I could do it there. We could solve that problem. Another logical choice might be right here. Might be at the ground where the ball leaves. I could also choose it to be over here. Like I said, it doesn't really matter, but usually there's an obvious logical choice. At least it's got to be somewhere where the ball starts or where the ball ends or something like that. But again, it doesn't matter, but you need to make sure that this stuff reflects your choice of origin. This all depends on where you decide the origin is going to be. Right? Sometimes that makes the problem hard. But once you get to this point, like I've said several times, you're pretty much done. Okay, so we're after y final. Our y side of the equation looks a little bit better. We've got a couple question marks here. I don't know a time. I left that out. The only thing I know is acceleration, so I can't do anything with y just yet. So just like before, I need to figure out a time first. I'm going to find the time it takes to get from here to here using my x equation. Right? So I got to use x first, and then I got to switch over to y. All right, so I'm going to use the same equation I've used already many times today. I should just start changing. Every time I do VOX, I should just start writing it that way. That's a plus 1/2 axt squared. Once again, acceleration is 0. Initial position 0. This all looks very familiar. If I solve for time, I've got time is equal to x divided by my initial velocity in the x direction. Now I'm just going to fill in some numbers. I didn't convert this. 60.5 feet. Ooh, I don't have any room. I'll do it over here. 60.5 feet. And we got to convert to meters. We got 1 meter in 3.2 feet. I would give you this conversion. It's 3.28 if I want to be specific, but that one I'd give you. I don't expect you to remember that one. You should know it's roughly 3, but I would give you that one. But like I said, any conversion with like time, seconds to minutes, obviously you should be able to do that. And anything with prefixes, you should be able to do those. All right, so 60 feet divided by 3.2 feet per meter gives me meters on top, which I like. And then my initial velocity is my initial velocity is 5.4 meters per second. My meters cancel out. I'm left with 1/1 seconds, so seconds on the top. Units are correct. If I solve that for seconds, what did I get? 0.408 seconds. 0.408 seconds. All right, so that's the amount of time it takes to get from here to here, which, people throw at 101 miles per hour. So there's not a heck of a lot of reaction time for the pitcher. I think or for the batter. That kind of says a lot. Now, of course, in real life, there is some air resistance, so it slows down a bit by the time it gets over the plate. But there isn't a whole lot going on, so there is not a lot of time to react to a fastball. But that's beside the point. That was the x direction. We know the time. Now we can switch over to the y direction. I know not very much. I can throw in time in the mix here. I know an acceleration. I want to find my final position. So once again, using the same sort of equation, my final y position is equal to my initial y position plus my initial y velocity times time plus 1/2 AYT squared. We use this equation so much. All right, that's the name of the game in projectile motion. We're looking for distances or displacements. Okay, so my initial y velocity was 0. My initial y position was also 0, so I'm left with a nice equation that's not a quadratic, which is good. Well, there is a squared here, but I can solve that because I'm plugging in t. So my final y position is equal to 1/2 times -9.8 meters per second squared times 0.408 seconds squared. I look at this and I say, hey, I've got a negative sign here. My answer is going to be negative, which I'm really happy about because we said when I started the problem that y should be negative. So I know I'm good even before I run the numbers. When you do run the numbers, you get negative 0.815 feet. I'm sorry, not feet. Meters. And if you do convert that to feet, it's about negative 2.68 feet. All right, so negative 0.8 meters, does that seem reasonable? How high? He's throwing the ball from, he's throwing the ball from what, roughly 5.5 feet up or something like that, well, plus the mound, so it drops by a couple feet. That seems pretty reasonable. In real life, there's other things going on because the ball's curving and stuff like that, but if you want to learn about that, you have to take my computational physics class. So that seems okay. So I'm happy with that answer. So this is the problem then. Let me get to it in my notes. And this problem is actually something that we spend more time on in our slightly more advanced class for physics majors. It's the same exact thing we've been working on. We're just going to sort of ignore numbers. And the way that I'm going to do this, what I hope is that if you can understand how I do this and you can understand all the steps in this problem, you're really going to be good for doing 2D kinematics. So if you can get this, if you can follow it, if you can go home and redo it, then you're going to be in good shape. So the example is this, and I'm going to turn to the keyboard again to speed up the process. We have a monkey that escapes the zoo. And climbs up in a tree to hide out. A zookeeper tracks him down and fires a tranq dart. I'm going to tranq dart, not dart, directly at the monkey, who lets go at exactly the same time. And I want to know generally what happens. So a monkey escapes the zoo, climbs a tree, zookeeper tracks him down, fires a tranquilizer dart at the monkey, straight at the monkey, and then the monkey lets go of the tree exactly at that instant when the zookeeper fires the dart. So the picture then looks something like this. Okay, got to get used to that. So here's the ground. That's a bad ground. Let's try another ground. And because I can't draw people lying down in the prone position firing darts, I'm just going to sort of draw the end of the gun. The dart comes out of the gun. It's aimed directly at the monkey who's hanging on a tree branch. All right, so this dart is aimed directly at the monkey. Now, based on what you know of physics and your intuition, if you aim that dart at the monkey and the monkey doesn't let go, is he going to hit the monkey? Yeah. If the monkey doesn't let go, yeah. Or what's the trajectory of the dart? Is it a straight line? No, it's a parabola. So depending on how fast the tranq dart goes, it might, if it's going really fast, then it's going to hit him, but it's a parabola, so let's assume that it's not because it's going to fall. It's going to fall and I want to go back to the ground. All right? So the question, though, is what happens if the monkey lets go? Right, so the monkey's going to let go of the tree at the exact same instant. So this is a little bit tricky because why? Well, we have two things going on here. We have two projectiles. One projectile is the dart. One projectile is the monkey. All right, and we need to sort of solve and see what happens to each of those things. The monkey is the easier one because the monkey doesn't move in the horizontal direction at all. The monkey just falls straight down, so it has no x motion at all, which reminds me to define a coordinate axis here. The dart's a little bit more complicated. It's a real projectile moving in both the x direction and the y direction. So that said, let me look at the monkey first. All right? So the monkey, like I just said, drops straight down. And so that means I don't have anything going on in the x direction. I can just look at the y direction. And all I want to know, all I'm really interested in is how far does the monkey drop? So if I write down my equation for the monkey, the final position of the monkey is equal to the initial position of the monkey plus VOT of the monkey plus 1/2 AT squared of the monkey. This term is 0 because initially it has no velocity. And this term, we do have an acceleration. It's just the acceleration due to gravity. And I'm going to say that it does have an initial position because I'm going to define my coordinate system to be right here. So that's my origin. All right. Just to declutterize this, I'm going to do that. So I have an actual axis. I'm just going to erase this so we get rid of some of the clutter here. All right, if I choose this to be my origin, and I say that the distance from the monkey to the tranq dart, this distance in the x direction is d, what is the height of the monkey? What is y initial? Whoop. If I give you this angle, we'll call it theta. Good. So using trig, just like before, you can draw a right triangle here, which I've already done with this dash line. So there's a right triangle. I have this angle. The angle opposite to that is y naught. And I have the adjacent angle. So if I have the opposite and the adjacent, that means I'm using tangent. If you solve your trig identity, you should get y naught is equal to d times tangent theta. Yeah, Shane?
Isn't it a parabola or like an arc back?
It is an arc. So the actual trajectory of the bullet is an arc, right? We're not talking about the dart yet. All we're talking about is the monkey. But I'm just trying to figure out how the distances relate to where the tranq dart's fired from. Okay? So I'm looking for the height of the monkey right here. And I could, if I know this distance and the angle that the gun shot at, which is this angle theta, then that's a triangle. But no, you're right. The motion of the dart is going to follow some parabola. So I wouldn't be using any trig if there's any parabolas involved. Okay, but in this case, I can draw that triangle and I'm good. All right, so I know my initial height. And so I can figure out then that the final height of the monkey is equal to d tangent theta minus, I guess we'll just write it in terms of g. G minus 1/2 g times t squared. So I'm leaving everything in terms of variables. Okay? All right, y sub m for short. So that's all I can do with the monkey. So now I can go ahead and look at the dart. All right, so the dart is a little bit more complicated. It has some x and y motion. I'm going to take a look at the x motion first because I don't really know a whole lot about the dart. But I do know a distance. I know this distance, d. I'm assuming that I gave you that distance. So I know that distance is related to the monkey because it's got to go that distance d before it hits the monkey. So in the x direction, then, I know that my initial velocity is equal to in the x direction is equal to the initial velocity times the cosine of theta. Okay, so this dart has initial velocity VO, so this is my x component. Not x. My final velocity is the exact same thing. It's a projectile, so it's not accelerating in the x direction. My initial position is 0. My final position is equal to capital D. All right? So if I solve for the final position, or actually what I want to solve for is time, I can use the equation that we've been using over and over again, plus 1/2 ax times time squared. Again, there is no acceleration, so that goes to 0. My initial position is 0. So x is equal to v naught times t. Yes?
How did you get the v naught cosine theta for the initial velocity?
So just like we've been doing before, I say that the initial velocity is v naught. That's just the vector velocity of the dart. So I make another triangle here. So if I'll draw the triangle. What I have is that guy is v naught. I gave you this angle is theta. So if I break this up into its components, into x and y components, I get this triangle. So this side is VO cosine theta. And this side is VO times sine theta. All right, so this side is the x component, this side is the y component. Okay. All right, so back to our equation. We're just solving for time now. So time is equal to x divided by v naught, where x, I already said, well, that's just d. And then v naught in the x direction is v naught times cosine of theta. All right, so I've solved for a time. Now let me stop and let's actually talk about what this time is. All right, so the time that I've given you is the time it takes for the dart to go from here to the horizontal position of the monkey. That's how long it takes to go from here to here. I don't know anything about the vertical yet, but I know that after d divided by v naught times cosine theta seconds, it's at least going to be somewhere along, this sort of vertical line. It's going to be somewhere in there. So at least it's to that position. Now the question is, I want to know how far the dart has fallen during that time. I want to figure out, well, what's the final y position of the dart? And how does that compare to the final y position of the monkey, which I've already solved for. I've already solved for the y position of the monkey. So I'm going to be a little bit tricky about that. We're going to look at the y direction. All right. Again, I'm going to write out everything I know using my coordinate system. My initial y is 0. My final y, I don't know. My initial velocity in the y direction is equal to v naught times the sine of theta. My final y velocity, I don't know. And then my acceleration is equal to negative g. Negative g. All right, and then I do know time. I just solved for time. Is that. Okay, so if I solve for my final y position then, I'm using the same equation. Oops. Oh, that was right. Y is equal to y naught plus vy naught and times time plus 1/2 ay times time squared. That guy is 0. This guy is not 0. That guy is not 0. So my solution then is v naught times sine of theta, if I just plug in what I found already, times time, minus 1/2 gt squared. All right, so that's what I have so far. Now, the interesting thing is I want to compare these two numbers, or these two answers. So here's my final y position of the monkey in the same exact coordinate system as the coordinate system I used for the dart. So if this thing is the same as this thing, well then the dart hits the monkey. So if I do that, all right, so the y of the dart is equal to v naught sine theta times t. I just solve for t using the x stuff. So after this many seconds, I know that the dart is at least at the horizontal position. So I'm going to put this t in here. So I get v naught times sine theta times time, which is d divided by v naught cosine theta, minus 1/2 gt squared. I'm just going to leave the t in there because that's what I did up here. So I have a term 1/2 gt squared. That term's the same. All right, now I'm going to go ahead and just clean this up a little bit. I get, v naught and v naught cancel out. So I get d times sine of theta divided by cosine of theta. Well, that's just d tangent theta minus 1/2 gt squared. So y of the dart, the position of the dart, the final position of the dart is equal to d times tangent theta minus 1/2 gt squared, which, if you noticed, is the exact same as the final position of the monkey. All right, so those two things are equivalent. This is kind of crazy. What this says, we didn't do anything with numbers here. All right, I just gave you an angle, a general angle. I gave you a general velocity. No specific numbers, no specific angles. What this says is it doesn't matter. It doesn't matter what the distance apart from the dart and the monkey are. It doesn't matter what angle, what initial angle, how high the monkey is. It doesn't matter how fast you shoot the dart. You always hit the monkey if the monkey lets go at the exact same time as you fire the dart. That's what this says, which is kind of
Velocity is projectile.
doesn't matter.
As long as the monkey lets go
At the exact same time,
directly at it, you'll hit it.
you'll hit it. Doesn't matter what the velocity is, which is kind of crazy, right? I mean, you think about it. If we draw a picture, if you shoot the dart really fast,
Go straight.
it goes straight. Maybe it curves a little bit. So here's the dart. We'll just put a barrel of a gun. All right, and the monkey, the monkey lets go from the tree branch. But if you shoot the dart really fast, it doesn't take very much time for it to go this distance, which means the monkey hasn't fallen very far in that time. Okay, so it hasn't fallen very far. Now if you shoot the dart really slow, so you get something more like this, well, now it takes a longer time for the dart to get from here to here, which means the monkey has more time to fall, which means that it's fallen this far. Okay, and you can keep drawing this picture.
It's always aimed at the monkey.
So the monkey has more time to fall, and the dart has more time to get there. Yeah, Clay.
So depending on the velocity of the dart depends on where the monkey gets hit when it's falling.
Yeah, that'll change the y position. I mean, the x position isn't going to change, but it's just going to change how far from the ground the monkey gets hit. The only way you don't hit the monkey is if the dart takes too long to get there or hits the ground first. That's basically the only way you don't hit it. Okay, so it's kind of counterintuitive, but the physics says that that's the case. That's what this equation says.